We are, all the committee is here, and I'd like to thank everyone who is attending the defense of Bayou Risanto, both in person and virtual. And the title of, can you just close, don't close it, but leave it cracked with the garbage can there. Yeah, leave it cracked with the garbage. Okay, so thank you all for attending. So for Bayou Risanto's defense entitled Improving Daily and Subseasonal Precipitation Forecast in Arid Regions through Convective Permitting Modeling and Data Assimilation. So a little bit of background and comments from me as his major advisor. Bayou got his bachelor's in arts in 2007 from Yogyakarta School of Philosophy in Indonesia. He got his master's in arts in 2012 in theology from Sanata Dharma University in Indonesia. And then he left Indonesia and came to the United States to pursue studies in atmospheric sciences at Creighton in Nebraska, where he got his master's in science in 2016. And his thesis research at Creighton was the interannual variability of nocturnal low-level jet cloud and low-level jet occurrences over northern Australia and Indonesia. Then he came to hydrology and atmospheric sciences here at the U of A in 2017 to pursue graduate studies in atmospheric sciences. So today, we're going to see the results of 3 of his dissertation-related articles. So the articles are one that has been published in the journal Atmosphere, another which was very recently published in Monthly Weather Review, and then another one which is still in review and has been submitted to Climate Dynamics. So the overall theme of Bayou's research has been regional convective permitting modeling to improve weather forecasts and subseasonal to seasonal forecasts. So this has, I think, from my perspective, 2 very unique aspects. The first is that the geographic foci for both of these works has been outside of the United States, which I think is a little unusual. So specifically, he's going to be focusing on the area of Northwest Mexico and also the Kingdom of Saudi Arabia. So we're looking at how we can better represent and forecast extreme precipitation events that are largely attributable to organized convection. So we're going to hear a lot about that today. And I think because it has this international flavor, this work is really exemplary of the university efforts here to motivate international collaborative research. And that is especially in including partnership with Mexico. So we want to certainly acknowledge the internal support from the University of Arizona to support Bayou's Ph.D. studies here. The second aspect is that this work has developed, in my opinion, what I think is very important innovations in 2 things. First, the use of GPS meteorology to improve short-term numerical weather prediction forecasts. And the second is convective permitting modeling to improve subseasonal forecasts. So you'll hear about both of these topics extensively in the defense. And I say they're important because both of these things, since Bayou has gone to meetings and published his papers on these subjects, they're now getting a lot of attention, both nationally and internationally. And so I think that's very much to your credit. So I'd also like to note that Bayou has been the recipient of several awards here during his time at the U of A, including the Kreider Scholarship within the Department of Hydrology and Atmospheric Sciences. He's also received the Galileo Circle Award from the College of Science. So these awards not only reflect the high caliber of research that I think Bayou has done, but I think more importantly, it also speaks to the fact that he's very hardworking and collaborative. And he's really established himself in our research group as an intellectual resource. And I think I'm more appreciative, though, that he's been a mentor and a good friend to all of us. And one final note, an interesting fact,
is Bayou is also an ordained priest of the Catholic faith in the Jesuit order. And as such, I'd like to acknowledge the support and kinship of his faith community while he has been here in Tucson all of these years, particularly his brothers at Jesuit House. Thank you all for all the support you provided Bayou while he's been here. And I will turn the floor over to you, and I wish you luck.
Chris, before that, he was also excellent in my class. And he did a great project. And contributed to one of the papers I meant by yes, but he did a lot.
It was cited how many times already? It's a lot. Okay, so let's start now.
Yes.
Okay, so to my committee members, Dr. Chris Castro and Api Irayano, Dr. Bill Smith, and Ayat Atala, thank you so much for giving me the opportunity to present my studies. So this has been this is the 5th year, I think, of my my study here and my work here. And I'm proudly offer you this it's kind of an overview of my studies. So as Dr. Castro mentioned, the title of my dissertation, Improving Daily and Subseasonal Precipitation Forecasts in Arid Regions through Convective Permitting Modeling and Data Assimilation. In the context of the changing of climates, we have seen increasing intense rainfall and flash flooding from convective activities, both in Arizona and Northwest Mexico, and also in Saudi Arabia, in the Arabian Peninsula in general. These two regions have the same characteristics. So they are arid and semi-arid environment and climates, and the soil has low infiltration capacity. The rain mostly comes from the convective activities. Extreme precipitation cause fatalities, infrastructure damage, costing billions of dollars every year. And the last note is that there's growing population in big cities in this area, like Phoenix, Tucson, we can see also Hermosillo, and also Jeddah in Saudi Arabia. Oh, sorry. So there are a need of reliable forecast systems that can provide early warnings for the communities, and also emergency and water resource management in that area. So this dissertation consists of 2 studies that are published in 3 papers that have mentioned by Dr. Castro. So the first study is about forecasting North American monsoon, so NAM, I just will call it NAM, precipitation over Northwest Mexico and the potential value added using the data assimilation. And then the second study is about forecasting cool season precipitation at subseasonal timescales over the Arabian Peninsula. So this also we investigate the forecast capabilities at 2 to 3 weeks lead time. It means that you start the initiation 3 weeks ahead of time of the event. And the goals are evaluating the NAM precipitation forecast over Northwest Mexico, generated by convective permitting numerical weather prediction and WP models, and then improving the NAM precipitation forecast over Northwest Mexico by assimilating observed precipitable water vapor, or PWV. So this is the total column of moisture in the atmosphere into the convective permitting model. And lastly, improving cool season precipitation forecast over Saudi Arabian Peninsula at subseasonal timescales using convective permitting modeling. So the core objectives of these studies are to understand convective extremes and improving the forecast capabilities over arid and semi-arid regions or desert using convective permitting modeling. So let's go to the first paper. The title is Evaluating Forecast Skills of Moisture from Convective Permitting Dwarf PRW Modeling during the 2017 North American monsoon season. So this work examines the ability of dwarf or weather research and forecasting models to simulate moisture and precipitation during the NAM GPS hydrometeorological network field campaign in 2017. And this has been published in Atmosphere in 2019. So we have a problem here. So the problem is the convective permitting does not adequately resolve the diurnal cycles of the convection and do not properly represent the convection in North American monsoon. So on the left, the figure on the left is the observation from GPM. So this is the global precipitation measurement. It's a satellite final version from August 10 at 6 UTC. So if you see here the bluish color are the precipitation measured at that time, and the lining, the red lining, is the extent of the clouds over there. On the right side is the dwarf GFS. So this is the global forecast system downscale at 6 UTC on the same day, okay, August 10. So there are relatively fewer resources or observational data in this region. So this region is Baja California and then Gulf of Mexico. Gulf of California, Baja California, and Northwest Mexico. Okay, so there are few sources of observational data to be assimilated to the model. So we have this problem. So in 2017, during summer, we have field campaign in this area. So we have the dots there are the sites that we set up our measurement. So for this particular studies, I use the data from June 30th to September 12th. We are collecting precipitated water vapor or PWV. I just call it GPS PWV from 18 sites. So this is double the size of the Transect field campaign in 2013 in the same area. We also collected precipitation data from 16 sites plus additional 7 sites from the Panagua and other surface meteorological data. We also look at the satellite precipitation. We consider 4 of them. So GPM Emerge Early, GPM Final, SMORPH, and Persian. And here in the picture here are Dave Adams, our colleague, and also Lourdes is there, and 2 other guys. And in the middle is the GPS antenna. So GPS antenna actually measuring the signals from the satellite. So the delay of the signals is calculated to be the moisture, the column of moisture in the atmosphere. Because when you have signal from the satellite, it's attenuated by the moisture, the water in the atmosphere. Right? So we calculate that one from this delay. So for the ground reference of our model validation, we use this for we considering this for satellites precipitation data, and we calculate the RMSE and the bias against the measurement from the sites. So we extracted the pixel from the satellite and compared to the sites measurement, and we use the RMSE and bias. And what we found here is that the GPM final has the lowest RMSE, as you can see in the value in the figure and the middle second to the left. And this agree with Zhang 2018 and also Kim 2017. Well, but the bias and RMSE, because we want the lower, right? But they are not really consistent in the pattern and the which one is the lowest one. And then we classify the active monsoon from June 30th to September 12th. Based on the inverted trough, the presence and the absence of inverted trough, and the monsoon extremes. So on top, the one on the left is what we call it the inverted trough pattern. So what we found there is that there's low pressure on dynamic tropopause marked by the warmer areas, the yellow one, And if you can see the pattern of the wind is a counterclockwise. So that is the inverted trough. But on the right side, we don't see it. So this is the one on the left, we call it the strongly forced day, and the one on the left, the one on the right, without the inverted trough, we call it the weakly forced day. So based on this classification, we find 9 strongly forced days and 39 weakly forced days. So I just call it 9 strong and 39 weak. And both of them can create these big convective systems in the areas. Mocker in 2018 and 2019 found that it is challenging to forecast precipitation during the weakly forced day. So based on that, we choose these weakly forced days and evaluate this one and also the strongly forced day. We use the advanced version of weather research forecasting, version 3.9, with 3 domains, 30, 10, and 2.5 kilometers from the bigger to the smaller one. And we use GFS, the global forecast system, and also the North American mesoscale model for the forcing of the model. In this presentation, I would like to highlight only the GFS. And the scheme we applied here for domain 1 is Kinetic, domain 2 is also Kinetic, but we left blank for domain 3 because it's convective permitting. Okay, so we simulate all 39 and 9 days for this one, and we're calculating the precipitable water vapor or PWV from the WRF simulation based on this one. Why? Because the model does not output the PWV automatically, so we need to calculate it separately using the Q vapor and also the pressure. So the Q vapor here is specific humidity, so we have to calculate that separately as well. Q vapor over 1 plus Q vapor is the specific humidity. And we then compare the GPS PWV from the observation from campaign with the WRF GPS PWV. And this is the result extracted from sites. So there are 18 sites, I remind you. So on top is the diurnal PWV. So the WRF GFS, the model, is the red line. And then the observed one, the GPS PWV, and the blue line. And then the first A is a combined, so 39 plus 9, so 48 days. And then B is only the weak, and then C is the strong. And then on the bottom is the diurnal precipitation from the 18 sites. WRF is the red one, and then rain gauge is the blue one, and the GPM satellite is the black one. What we see here is the WRF GFS show wet bias in PWV. So WRF, you see the value is higher, right? And then the model PWV becomes out of phase after 6 hours. So if you see the pattern, it's kind of off after 6 hours. And model result precipitation is within the range of the gauge. So I put the gray shades there. So the gray shade is the standard error. So they are all within that standard error and disagree with the modeling papers, for instance, from Mocker 2018. And the combined and weakly forced days result have similar pattern because of the numbers, because one is 9, the other is 39. Okay, let's look at the domain wide of the precipitation. So this is 3-hourly precipitation from 12 UTC to another 12 UTC the next day. On top is the WRF GFS, and then GPM finals in the middle, and the difference is the one in the bottom. So WRF GFS minus GPM final. So what we see here is that the WRF GFS initiates and terminates rain earlier than the satellite observation. How we know that? We see the bluish one on the second, on the third figure to the left. I mean the one in the bottom. So blue means that the WRF is wetter than the satellite, right? So but at the end, like around 6 UTC, you see there is no more blue, and that one is more red. So actually the GFS, the WRF GFS does not continue the rain, so stop the rain, while the observation still seeing the ongoing rain. And also the model underestimate the westward convective propagation. So if you see that in the one that I circled that one, so there is the propagation actually of the convective system toward the Gulf of California, but then the model doesn't see that. Okay, so in order to quantify this result, we use the forecast scale evaluation using verification metric. So this is categorical statistic. So I use critical success index, CSI, probability of detection (POD) and false alarm rate or FAR. And this is based on the contingency table criteria. So the one in the middle. So that is the how we calculate the hit, the miss, false alarm, true negative, and then we calculate the CSI, POD, and FAR. So precipitation event is defined as the total accumulation at least 2.5 millimeters in a grid point in 6 hourly or 10 millimeters in daily periods. And a good forecast scale is defined when POD and CSI and 1 minus FAR are approaching 1 because the value is from 0 to 1. So if it's grading to 1, it's good. And then good forecast scale also when the difference, for instance, CSI strong day minus the CSI weak is positive. Then this is also good forecast for the strong, okay, but bad for the weak. So we also calculate this field significance there using Monte Carlo technique. So here's the result for the WRF DFS and also for the WRF NAM, for CSI strong minus weak. So we see now blue, right? Blue near the Gulf of California. So it means what? It means poor forecast skill for the weekly force day, but it's good for the strongly. But it's bad for the weekly force day, for the 39 events that we look for. And also, forecast is poor over lower elevation along the west coast of SMO. So SMO is the Sierra Madre Occidental, the lining there, where the MCSs propagate. So this one, the finding here agree with Mocker 2018. Also, we calculate sensitivity analysis based on this equation. So this is regression in statistics. So what we calculated the covariance over the variance. And what is sensitivity? Sensitivity is how much change of a particular variable we'll have in the later forecast hour if we change the initial PWV in the initial time. Okay, so that is sensitivity. So what we are testing is based on the site location. So we have 18 sites, I think 7 in the coastal area and 11 in the mountainous area. So we use 500 meters above sea level threshold for this one. So here's the result, PWV sensitivity. So on top is the August 9 case. So this is the weak case, and then the one in the bottom is the strong case, 27 July. And I put the regression, and then also the mountainous and the coastal area sensitivity analysis. So what we found here is the PWV is more sensitive to the change of initial PWV in the coastal sites, right? So if you see the pattern there also show that it's more, you have more color there, and also the value 0.25 is greater than minus 0.01, right? Also for the strong case is higher value, and also resembles with the EF regression map. How about precipitation sensitivity? So here is the sensitivity of the precipitation. On top is the coastal, and then the one in the bottom is the mountainous for the weak and the strong case, the 9th of August and 27th July. What we found here is precipitation is more sensitive to the change of initial PWV in the mountainous side. It's not in the coastal, but in the mountains. So you see that in the figure there in the bottom. So all of them have higher values of sensitivity. So conclusion. I have two conclusions here, forecast capability and the forecast sensitivity. The first one is that the WRF model initiates and terminates precipitation earlier than the observation based on the satellite and also rain gauges. And then the WRF model underestimates the westward propagation of the convective system and exhibit relatively low forecast skills during weekdays. For the sensitivity, model PWV is sensitive to the changes in initial PWV in the coastal sites, and model precipitation and moisture flux convergence that I do not show here in the slides, but they are sensitive to the changes in initial PWV in the mountainous site. So at the end, I have hypothesis constraining initial condition of moisture via data simulation will potentially improve forecast skill of rain or precipitation. Let me take a break first. All right. So this is the second paper. The title is The Impact of Assimilating GPS Precipitable Water Vapor in Convective Permitting WRF ARW on North American Monsoon Precipitation Forecast over Northwest Mexico. So this work is to assess the impact of GPS PWP data simulation on short-range NAM precipitation forecast across 38 days with weak synoptic forcing. So this is only the weekly force day that I'm using during the NAM GPS field campaign in 2017 over Northwest Mexico. And this is what Dr. Castro had mentioned and we published in monthly weather review last month. So what is data simulation? What kind of creature is this? Data simulation is a technique of correcting prior knowledge. It can be like state variables in NWP, using observation to obtain an estimate of the true state of the system and the uncertainty or the error of the estimate. And this technique involves statistical analysis based on Bayesian statistics, and is applied in Kalman filter. So the software or the code can be downloaded here for free, thanks to Anderson and Friends, 2009 and 2001. And the figure there is how we picture it, okay? So if you have a state variable prior, like prior state variables, you have this, the one on green. So this is the distribution, right? And then you observe in nature, then you have another distribution, which is the observed, the one red. And then you want to correct this with this software or this calculation. Then you will have the posterior PDF. So this is the updated variables that you need. And then you can use that one. So the equation is actually the basic of the Bayesian statistics. All right. So what we are assimilating, again, GPS PWP from the global positioning system antennas that here Dave Adams are setting up in Kino Sonora. And this GPS PWP is every 5 minutes. It's amazing. So you can make it like during storm, during clear sky, no matter what the weather is there. And then how far does this data, if you put in the model, influence the grid points in the model? So that is the picture and on the right side. So if you put like one side for PDP, then is the circle there. The farther it is, the less, the fewer influence you will get in the model, right? But I have 18, so I make the convolution of this, merge it together, and then I got this the circles there that show how far it is. So actually, the area that gets most influenced by the data is the one in the middle, the one with the bold circle, and that's what I call it DC11. And this is based, so this setting is based on the observation error of 0.075 centimeters, and the Gaspari-Cohn covariance localization length is 0.607. So that the Gaspari-Cohn can be translated into horizontal distance of 440 kilometers, and the vertical distance about 7 kilometers. Now, we need to test this one first, because different areas, different setting, I bet. So we're testing this configuration, that configuration. So I'm using the August 9 case, the one that I show you again and again here, using 30 ensemble members. So I have experiment 1 through 5, and each experiment starting from different time. So there are some like 0 UTC, and then 6 UTC, and 18 UTC, and then spin it for 6 hours so that it has stabilized the, not stabilized, but the perturbation going to the core domain. And then the DA, the data simulation cycle, is also differs from one to another. So there's one like 6 hourly, and then 12 hourly, and then 18 hourly. And then stop after that, take the ensemble mean of the set variables, and then run the deterministic forecast for like this one, like 18 hours, 12 hours, and 24 hours, up to 12 UTC the next day. Then what we found here, this is the root mean square of error of the PWP from 18 sites. I checked all 18 sites. The star indicates the beginning of the DL simulation. So we want it low error, right? We want low RMSE. So we should see after the stars, the RMSE getting lower, and then the diamonds there is the end of the assimilation, and then the starting point of the deterministic. So if you see on the gray side there, between 17 UTC to 01 UTC. You see that one is the black one is experiment number 2. So what we found there, lowest RMSE at the forecast initial time. So the diamond is the lowest, and then the slowest RMSE increase in the forecast mode. So you see it's increased relatively slower than other experiments, right? And this is an improvement of model's memory of PWV. So there is a issue of model memory of PWV from Mocker 2019. So we try to solve that one too. All right. So how about the total precipitation? How that impacted by the PWV? And this from all experiment plus the GPMF on the left is the 24-hour total precipitation. And I take the lining of 25 millimeters, all the black line there, 25 millimeters, and I want to see how much rain that actually fall in that curve for each experiment. And I found experiment 2 is the best, 16.7%. Well, I wish that it was 17%. Exactly like, yay, that's good. So again, this is from August 9, 2017. So we choose experimental configuration with this one. So 6-hour spin up, 12-hour DA cycle, and 18-hour deterministic. With this configuration, number of ensemble, I keep it 30 members. So I perturb the initial condition. I think there are 6 or 7 set variables that is perturbed. And then we simulated all 38 days. So this is actually the weekly force days of the cases that we have. And then we also run the control run. So we thought that assimilation, all the same, except the blue line is not there. So we don't use the assimilation. So we call it the no DA forecast. And the other one is DA forecast. Okay, after we simulate all of them, then we check the PWV statistical analysis. So A is the mean, so we see there, DA is the blue line, observation is the red, and then the no DA is the dash, the black dash. So what we see there, the GPS PW, the DA actually is closer to GPS PWV, but how significant is it statistically? So it's only like only a few hours there. 18 UTC is significant, and then 7, 8, 9, 10, 11 is significant. Others is like close to no DA. The RMSE looks good because the blue line, the DA is lower than the no DA. The bias also good, it's lower. Correlation is higher. So I think this is good too. But still, the problem is the out of phase is still there. If you see the blue line and the red line kind of off after 6 hours, that one is after 12 hours, I think. It's off. Now, how about the PWV in the domain Y? So here is 3-hourly PWV. On top is PWV of DA, and then the second one is no DA. The bottom is the difference, and I blow the no DA over the difference over the GC11, where there is a lot of observation sites there. Let's blow it up here. So what we see here, DA PWV is lower than no DA PWV. So starting at 21 UTC up to like 6 UTC is lower. So it's good. So we made it, right? So the no DA, we thought the depth simulation is like higher. And so the PWV wet bias is reduced in the DA. As you see in the value also, it's all minus. Now how about precipitation forecast? So this is again DA, no DA, and then the difference. Okay, DA minus no DA. Let's blow it up. There. Remember, we have problem with from 3 UTC, the precipitation is gone, right? So now we still have the precipitation here, which is positive, meaning the DA has more precipitation, but than the no DA, right? Precipitation rate is higher than the no DA at 3 to 9 UTC. So DA generates more precipitation than DA, especially in this area, GC11. And this one is the precipitation from sites, from all 18 sites. Let's see here. Sorry, there. So the black line is the GPMF. Blue line again is the DA, and then the red line is the gauge. So after 5 UTC to about 11 or 12 UTC, the precipitation is closer than the GPMF precipitation in the last 7 hours, right? And also within the range of the standard error. The standard error is marked by the gray shade area there. So the blue lines and the black lines, they are kind of closer, but we still have problems. I mean, because it's two different kind of measurement. That the gauge is 1 point measurement, and the other three is a pixel measurement. So the pixel is 10 by 10 kilometers, something like that. So it's very hard to make it fit. Again, we do the DA, I mean, the POD analysis. So POD DA minus POD no DA. So blue indicates high forecast skill for the DA precipitation forecast. So we have blue there at 18 UTC, and then again at 3, and then 6, and then 9 UTC. The values of the average value is positive only after 6 UTC, right? So all positive only. So the DA is performs better than the no DA. And this one is again measured, not measured, but calculated against the GPM precipitation data set. But we have to prove it. Well, this precipitation is good. Is it really good? Okay, let's look at the cloud top temperature. So on top is the DA, cloud top temperature, every hour from 2 UTC, and then no DA, and then the difference. So what we expect, what we want is that the DA should have colder cloud top temperature. When it's colder, the cloud is deeper, more rain you get, you know. So here we found that the DA actually good because now we have all the blue shade there. It means it's lower temperature. DA is colder than the no DA at 4 and then 5 and 6 UTC. And this match with the precipitation DA forecast because you have more rain. So the cloud of temperature must be higher, so the cloud must be deeper. And then how about the mu K, or most unstable convective available potential energy? Let's take a look here. Let's blow that up. So this is the difference between DA and non-DA. So we want the mu K should be higher, okay? Because you need energy to boost the moisture from the surface to the atmosphere. So what we found here, higher mu K in the DA, especially at 00 UTC to about 6 UTC. So this is approximately 3 hours before the precipitation, and it agrees with GPS data, GPS PWV DA impact. So it means also when you have more mu K, it's unstable. The atmosphere is unstable. And the next is the dew point. We want to see this one too. Let's blow it up. All right. So here again, the dew point is higher than the no DA. The dew point here, all positive values offer the GC11. And this is about 9 hours before precipitation, and it's again agree with the GPS PWV impact. Higher dew points means more near surface moisture and higher instability in the DA forecast. Now, here's the finding. This is a summary. Actually, you just need to understand this one. So on top is the DA forecast, and below is the no DA. Okay. So if you have GPS in your area and then you want to model it, you know, forecast it, you increase the moisture near the surface. Okay. When you increase the moisture, increase in stability, you build deeper clouds, and then later on, you have more intense precipitation, right? If you don't have, then it's dry. Decrease moisture, decrease moisture near the surface, the instability is slow, and then maybe you can have clouds, but it's not deep enough. Precipitation is maybe kind of dry. Okay, so the finding summary. So the GPS PWV simulation exhibit an impact on atmospheric preconditioning and the precipitation. So we precondition the atmosphere in the initial state. Right? So in conclusion, DA spin up improved models memory of PWV. The area of high density of observation, the GC11, has the most improved forecast, as we show, we have seen in the previous slides. And the DA forecast adjusts the model PWV closer to the observed data, but still, we still have the problem of out of phase, right? So it's kind of off. And the DA forecast preserve model precipitation timing. After 3 UTC, you still can see the precipitation. And the DA does not necessarily improve the magnitude of the model precipitation and westward propagation. So we still need to investigate this one. And it seems there are other mechanisms and processes in the atmosphere that also drive the precipitation. Right. So the last one. So this is the last paper, number 3. So the title is Retrospective Subseasonal Forecast of Extreme Precipitation Events in the Arabian Peninsula using Convective Permitting Modeling. So this work is to demonstrate the potential extreme during the winter season, and then also at subseasonal time scale, and then identify the region and periods of forecast opportunity, investigate the predictability of synoptic scale. And this is a collaboration between University of Arizona and King Abdullah University of Science and Technology housed in Tual, Saudi Arabia. And as has been said, this work has been submitted to Climate Dynamics and still under review. So the motivation for this work is there are 3 parts here. Extreme precipitation event during during winter in AP are generated by MCSs. Okay, and then precipitation cause weather-related catastrophic hazards costing billions of dollars every year, and the events closely associated with intense extratropical events. So we do this experimental design. So we pick the top 21 extreme precipitation events in the AP from 1998 to 2018. And we simulate them using the CP-WRF, the Convective Permitting model, and the lateral boundary condition of the forcing is from the European Center of Medium Range Weather Forecast, Subseasonal to Seasonal Forecast, or ECMWF for forecast. I call this raw ECMWF. And then simulation initiated at 1, 2, and 3 weekly times. And the selection of the events of this 21 is based on the recorded rainfall over 20 millimeter per day near Jeddah from October to April. So this is the setting of our model. So it has 2 nested domains, so 12 kilometers, and the bigger one, and the smaller one is 4 kilometers resolution. And the cumulus scheme for the outer domain is from Grail Fritas. And then we also we test the CFS P2 in the beginning, but then we move to ECMWF for all our simulations. And the ground reference to validate our model, we consider 5 products. So GPM finals, more Persian, GSMAP, and also the last one is Gauss-Ray analysis. And we use 43 rain gauges out of 208. So this is very common. We have a lot of rain gauges, but maybe only 1/3 of it is good. From 2000 to 2012. And then we calculate, just like before, the RMSE and the bias of its satellite. And we found that the GFPMF has the lower bias. If you see that in the lower part, second to the left, the first one, sorry, the first one for the left is minus 0.2, right? So this is the lowest, but the RMSE is kind of the second lowest, I think. Yeah. But anyway, we also use the Gauss-Ray analysis because Gauss-Ray analysis has the higher spatial resolution. It's 5 kilometers. So it's good. Now we also use the classification for the dominant synoptic scale weather patterns in the region. So based on Luong 2020, we found that there's extratropical pattern, transitional pattern, and the tropical pattern. So from 21, we have 10 belongs to extratropical, 3 to transitional, and 8 to the tropical. Okay, so we simulate all of them, all 21 with 11 ensemble members. And then here's the mean total precipitation between CP-WRF and the raw ECMWF for the extratropical events. So just use the 10. And what we found here, the one on the left column is for the 1 weekly times or week 1, and then lead 2 weeks lead time and 3 weeks lead time, or week 2 and week 3. And what we found here is that CP-WRF generate more precipitation in central Red Sea. Did you see that? Central Red Sea. And oh, by the way, the star there is the city of Jeddah. Okay. And Zagros Mountains also have is good generate more precipitation. It's red, so it's more at all the times. So from week 1 to week 3, it's good. Now the tropical one. So this is the 8 events that we have. So different from the previous one, this CP-WRF generate more precipitation in the central AP for the weekly times only. If you see that red, they are more red than in the difference in the lower left of the figure. And CP Ward kind of fails to represent precipitation in the central Red Sea at week 2 and week 3. So there's blue there. So it's not that good. CP Ward generate better precipitation over high terrain, especially in south of Jeddah or southeast of Jeddah, and also east coast of Sudan. So you see the reddish area there. Again, we do analysis with this one, PCSI, Ph.D, and minus FAR for all lead times. And this is for the extratropical. So what we have seen in the previous slides agree with this one. So precipitation forecast scale is high over the central Red Sea. So it's all blues, right? The west coast of AP and the Zagros Mountains at all the times. The tropical one also agree. So precipitation forecast scale higher over the central AP from week 1 and week 2, but not so. So it's higher. So higher for the ECM, the raw ECMWF, but not for the CP Ward. And the possible problem is that the model SST does not change significantly at subseasonal and short range forecasting time scales. So we still need to investigate more on this one, the problem here. So we also compare this against Kalsra analysis. So before it's against GPM, so it's Kalsra analysis. The result also the same for extratropical and the tropical, one from week 1 to week 3. Okay, so we do this one. This is very common in subseasonal forecasting evaluation using relative operating characteristic. So this analysis classifies the forecast into hit and misses based on the observation and at predetermined threshold. So we use threshold 20 millimeters here. So it's usually plotted as a POD versus FAR in Cartesian coordinates. So if your model is good, the curve will approach the upper left side of the Cartesian coordinates. If it is no scale or kind of bad, then it will be below, usually below the diagonal, the dash, the red dash line there, the diagonal. So it's bad. So we do this one for all events. Okay, so the extratropical and the tropical, and we compare the raw ECMWF on the left and the CP Ward on the right. For week 1, week 2, and week 3. So the raw indicating the week in times. And what we found here is that forecast probability improved from no scale in raw ECMWF. You see that the curve is not that good in the raw ECMWF for all. But the CP Ward show there's a curve toward the upper left corner of the figure. So we also calculate the AOC, which is the this one, the rock curve, area under the rock curve. So between 1 to 0, from 0 to 1. So most of them are above 0.5. And then lastly, we do this one geopotential height forecast for the 800 hectopascal and 850 hectopascal. We compare the extratropical against tropical. In the 500 hectopascal on the left, we see that the correlation coefficient is consistently higher for the extratropical events than the tropical. So you see the R there values. The extratropical is higher for week 1, week 2, and week 3, right? But in the 850, the extratropical will be higher at week 1, and then at week 2 and week 3, it's kind of, it's not kind, but it's really lower than the tropical. So it seems that this 850 hectopascal geopotential height is directly affected by the changes near the surface variables. Okay, so changing very rapidly and it's very hard to predict out of week 1. So in conclusion, the CP Ward demonstrates the potential improvement in forecasting full season precipitation at subseasonal time scale in the Arabian Peninsula, and 90% of the no-scale raw ECMWF improved to some reasonable scale at CP Ward. The AOC is greater than 0.5 out of 3 weekly times. And higher forecast capability of CP Ward depends on the domain synoptic patterns. In this case, we see the extratropical kind of, is better in performing that. Okay, so overall summary, convective permitting modeling enable us to understand the dynamics and thermodynamics processes of the convective system in arid regions. Coupling the convective permitting model with data simulation improves the non-precipitation forecast timing in Northwest Mexico. And also last one, convective permitting modeling demonstrates the added value of sub-seasonal forecast capability of extreme events at the AP. Acknowledgement, so my gratitude goes to Dr. Castro, Dr. Ariano, Sini Chang, Dr. Jimmy Walker. I don't think he's here, but I invited him. Dr. Tang Luang, Dr. Gramute, Modi is here. And also my research group at the University of Arizona and at House, and also I thank the Society of Jesus, especially the Vatican Observatory Jesuit Committee. Thank you so much.
Yeah. Okay, so Bayu, why don't you stop sharing your screen so we can see the folks online? How I'd like to do this is if you do have a question online, if you could raise your hand, and then we can go back and forth from folks in the physical room to the virtual room. So I'll start with the physical room for questions. And I would ask the committee members, hold your questions until the closed door. Yeah, go ahead.
So I understand that the P&KR models have inaccuracies with sample error of covariance. So is the purpose of this Gaspari cone covariance function is that localizing covariance across multiple state variables and then describing that as a function of distance? Is that what that is doing? And how is it constructed? Is it, you mentioned a convolution?
Yeah.
So could you describe more about that?
Okay, so the convolution actually, how did I calculate that? I use the only simple math to do that one. So I think I take all of them and then get the I think I get the mean. I forgot how to do that, but I have the codes if you want to see it. I can explain to you, but it's not the top of my mind now. And then this GC, the Gaspari cone, is actually it's kind of constructing the what you say, so the covariance within that area, right? So you have to set it up in a way that make sure that the influence of the data that you put in that particular pixel propagate to other pixels around it. But you cannot make it too small because otherwise you will not influence or affect the pixels out there. But if it is too large, it will not make sense, right? Yeah. So it's very, very hard. To be honest with you, these 0.07, we have tried many times. We have tried 0.1, 0.03, 0.05, 0.07. I think we tried 1 at one time. So I make this one with Jamie when Jamie was still here, testing different kind of this one. And eventually, Dr. Abe and I discussed this, and then we said, okay, make 0.07. I think it's good enough because there are 2 papers that calculate this thing. How to make sense of this one? I can send you the papers if you want, or Dr. Abe can send it to you. So with the network we have here, the average distance between one side and another is about 300 kilometers. Maybe that. So with this calculation, we found about like 400 kilometers, something like that. I put that, okay, that's in the, in the ballroom. So we use that one. But of course, when we take this to the reviewer say, oh, why you have one like this one, what's better? Well, because we have this network is, is very large, it's 300. And I bet the reviewers from Japan, because Japan is really good. The average distance is 20 kilometers, really good. So I wish we had that one, But as first project here in North Mexico, the result is, I mean, to me, it's, I mean, like, oh wow, it may impact, right? So it's good. So especially in the GC11 when we have denser network, then it's good. So what we have to do next time, if we want to try it again, you know, get more antennas, GPS antennas. So it's the average distance will be less than 100 kilometers. That would be good, I guess. Yeah.
Do we have any questions from the online audience? Yes, Steve, go ahead.
Sorry, I just submitted my question by chat,
Okay.
Oh,
but I'll rephrase it, restate it. So, yeah, I'm very impressed with the presentation for PhD defense today. My question is, do you have any idea for when you ran the data simulation experiments using GPS met reciprocal water vapor data, that you did not see any improvement in the skill in forecasting westward propagation of mesoscale convective systems off the Sierra Madre westward towards the Gulf of California? So why do you suspect that that failed to happen?
well, I really wish that the PWV assimilation impact this one too, right? That's what we want, but it doesn't happen. So what are other things that we are thinking is to look at the physics. We have discussed about this using the modified cartridge from our colleague Tang, who is now in Saudi Arabia. And we tried that one, but it's not successful yet because the scheme kind of computer dependent. So it works with Cray very well, but not with the Intel that we have here. So my suspicion is that of the physics, I think, in the model, in the work model. There is something there. That's my answer, Steve.
Thank you.
Yeah, we can try to look at to investigate the physics more if you want. That will be fun.
Other questions, either from the online or in-person audience?
Yes.
First of all, great work. I know how hard you worked on that. To a minor here, I'm a public health major, and I have a minor in animal, and bio helped me a lot to understand this. So thank you for that. I have tedious question. You started with the 39 and then you used only
Good.
just
I bet no one here noticed that. So in the first paper, I said 39 league cases, right? So but in the second one, there are 38. Oh, where is the other one? So the other one is from August 19. So I tried out to simulate that one again and again, and it was failed. Crash many times. You know, no matter how much I try to adjust the configuration, I think there is instability because when you assimilate a particular variables into the model, then it will change other variables too. Not only one variable change or the PW change, but also other things like the wind, the temperature may be changed, and can be made the simulation so unstable, and then the model just crashed because it doesn't make sense, right? It doesn't make sense that it's crashed. Yeah, so I just simulated the 38. Thank God it's only one crash. The other 38 is still working well.
so
Yeah.
I was expecting you missing that.
Yeah. Good.
Do we have time for a question or two more?
So you just correct me if I'm got it wrong. So you forecast up to 3 weeks,
Yes.
and then if you look at the first week, it was okay. Second week was
Oh yeah, decreasing.
third week was very bad, right? And then you compare the gauges and iron.
Yes. Yes.
I kind of forgot where you showed separately the scale of the first week, second week. See really the performance. Did you have it there to see?
Yeah, that's good question. We don't have that one because we make it discretely. It's not continuous. You know, if it is continuous, I can show that one. For instance, from week 3, you have initiation here, and then go to 3 weeks, right? Right. And then another one from maybe a day later, and then like that, right? And then day later, and then things like that. So we
basically x-axis is going to be lead time.
Yeah.
The y-axis is going to be.
Yes. We don't have that one yet.
So why you didn't make such a thing? But it's really important to understand how
That's true.
the forecast decay as a function of lead time.
Yeah, that's true. Shini and I actually talked about this already. I think there is one thing that I forget what's the hindrance there. But it's a good suggestion. I'll think about it. How to make that one happen.
Okay, that would be very useful.
Yes. Other papers that using this one, the one that you say, they have continuous every day. So the figure will be like smoothly like that, correct? But this one is discrete, so the figure will be like this, like that, something like that. This will not be pretty, but still you can see the decrease of the forecast still, of course.
The other question is, since you had fibers, still I'm not sure even if fibers is better than gauge. I guess gauge might be for 1 day analysis, probably is better than fiber. But we can discuss that later. You have fibers, it can give you some sort of pattern of precipitation. Yep. And I was wondering if you look at the images that you simulated and then compare the fiber to see if there is a systematic way of correcting the forecast. It might be some systematic patterns that are repeated. And the reason why I'm saying is I'm trying to see the opportunity for other techniques like machine learning, things like that can come and kind of glue in all this stuff that they did with some observation and then include in a model. And I want to see if you have thought of anything that contributed from techniques like this.
Yeah, that would be great. We have the GPM actually is good already in the plain, like if you don't have like mountainous complex terrain. But the complex terrain, especially here in the Sierra Madre Occidental, is kind of very hard to do that. Even the reviewer also asked us, so how true is this over the terrain? Because there are few papers out there that also have say about this, about how difficult it is to estimate the precipitation over the terrain. And this one comes out when we try to do this with over Sierra Madre, and also in our recent studies, our recent project over Chile, we also have problems in the Andes because they're so complex and it's very hard. So when June already, I think 2 years ago, she said that you can correct the GPMF using the she has the technique about this one in this paper in the Journal of Hydrometeorology. But it will, well, it can be done, but I think it'll just take more time for me to work on it before I can submit it to Master Review back then. So yeah. But thank you for the suggestion, and we can work on that one.
I'm gonna take one more question. Are there any more questions in the chat?
But I see it.
Okay. Is there any more questions from anyone in the audience? Okay. Then this will conclude the public portion of the defense. So we would like to thank all of the in-person and online attendees And have a good weekend.
Have a
So
good weekend.
you may stop the recording.
Good job, Bayu.
Thank you, Jenny.
Thank you.
Thank you.